Hey everyone, my name is Trent Kelly, and this is my second attempt at D208 predictive modeling. And to start out, we will restart and run the kernel. All right, and while that's loading in, we'll go over the table of contents here. So to start out, we're going to be going over a research question, describe logistic regression methods, summarizing data preparation process for the logistic regression, compare an initial and a reduced model, analyze a data set using the reduced model, and summarizing our findings. For the demonstration, the identification of the programming environment, this is Jupyter Notebooks. We will be comparing an initial and a reduced model, and then we will be interpreting the coefficients from that reduced model. My research question is, I just wanted to understand what factors or variables contribute to being overweight. The goal of my analysis is to further understand the variables that correlate to being overweight. The method justification, this is pulled directly from Statology, and I only needed 4. They did list 6. I just pulled the first 4 off of there. And importantly, what I do want to point out is the response variable is binary. And when we compare that to a linear regression model, the response variable in that linear model is going to be quantitative in nature. But this is categorically binary. So it's originating from a yes or no, true or false, and then we're converting that to a 0 or 1 for utilization in our model. And this is something that was marked for revision, so I do want to go over it in a little more detail. So the reason I selected Python for my language of choice, outside of it being simple syntax, it's what I have all my experience in, but Python especially excels with these models because of the libraries they have access to. So the scikit-learn library, very specifically, it's used frequently with machine learning, and this library is not available in the R environment. So this is one of the larger indications on why I used Python. Method justification. So explain why logistic regression is an appropriate technique to analyze research questions. So when we're looking at the type of question that we're asking, so since my y variable is a binary value, overweight, yes or no, 0 or 1, this is the most appropriate model for this question if we can accurately predict who is overweight. Describe your data cleaning goals. And so this part is reused from D208. And so these are all my libraries, importing my CSV file. And briefly, we'll go over this because we went over it in task 1. And so when I was doing D206, I noticed that when I started plotting these bar graphs, there were large spikes. And when I filled nulls, I filled them with the mean values, and that task did not get kicked back to me, so I just left it alone. But I knew I had to address it with this class. So instead of doing mean value fill, I changed it and I did forward fill, which forward fill just takes the last value before the null and fills it in for the null. And it's not always appropriate and applicable, but I felt for this it was, especially when we start looking like outliers and things like that. So this is evaluating the original CSV file. And this is the original data, how it plots, much different than that. So I'm doing forward fill, and that's how it looks after the forward fill. It's much more consistent with how the data originally presents itself, so I was happier with how that turned out and feel that we could move forward with using forward fill. And that should actually say income. I knew there were no duplicates from D206, but we reran it just to make sure. And describe function. So they all look good for the respective ranges. I am going to come back to this when we got something sent back to us on this. So I do want to come back to this and I'll discuss these in larger detail. One thing I can point out is one of the things that I will do is I'll look at values in respect to their columns and see if there's anything immediately unusual about it. So age, looking at the minimum age, and as long as it's not something largely negative or maximum that's outside of the normal human lifespan, or something like income, but I'll come back to this. Here we are converting yes to no to 1 to 0. If we recall from the logistic requirement, we have to have a binary value, so we need to change these to 0 to 1. And also with overweight, I noticed that there was a 0.709 value, so this is changing it to 1. And that way we have access to that more data. You could have went either way. You could have made that a 0, but I felt that it statistically was closer to 1, and so I just made it a 1. And then also needed to change overweight to an integer, which I believe I go over this in greater detail. But basically, overweight was coming out as 1.0 or 0.0, and I wanted it to be 0 and 1. So I changed that to an integer. So in conclusion, data cleaning, we changed the names of the items 1 through 8, which is right here. Didn't go over that. And replace null values with forward fill to reduce artifacts, change duplicate, check for duplicated values, and check for outliers, which again, I'll come back to the outliers. And here we'll go over outlier discussion. So this was also marked for review. And so this is where I declared my y variable and my x variables. And so what I'm looking at as far as the summary statistics here. So non-null count, mean, standard deviation, minimum, the quartile ranges, and maximum count. So specifically what I would be looking for like outliers and things like that when I'm looking at this from a statistical standpoint, especially the quantitative values, is going to be the quartile ranges and the standard deviation. So the standard deviation is looking at the variance, and we'll go over to some quantitative income. So the standard deviation is looking at the variance around the mean. And I think I have some other ones further down that will make it a little easier to visualize. In the quartile ranges, what I'm looking at for those with quantitative values is I want to make sure that nothing is too far outside of the mean. So I just want to make sure that these look pretty close to the mean, and it's kind of a quick way of identifying some of the variance with the upper and lower data points when you're looking at outliers. And here are the univariate and bivariate plots. So these are the univariate plots. and bivariate. All right, and data preparation. So describe your transformation goals that align with your research question and the steps used to transform the data to achieve the goals. This was done earlier to provide uniformity with the univariate bivariate plots, but changing like true or false to 0 and 1, just so in the plots we had 0, 1, not like some that were 0, 1, some were true and false, or yes or no. So that was done earlier. And we needed to change 2 of the names of the one-hot encoded variables, and this is done further down. And the reason that this was done is because when I was changing some of the code that I was using just to practice and work on things, I was getting errors with 2 names. So I changed them for consistency, and that cleared the errors. So this is just looking at the unaltered weight column since we did change the 0.79. So I was just looking to make sure something numerically had changed. And this is the altered overweight column. So we do have a change in the mean value at least, so I know that this was something had changed. And this is how it was originally formatting. So I wanted to change that to a 0 to 1. So this was changed to a 0, 1 earlier when we changed it to an integer. This is providing the CSV file of what we just did up there. And so an initial model from all independent variables that were identified in part C2. So what this is doing is one-hot encoding the categorical variables. I know we didn't technically need to do this, but since we had like complication, risk, and services, I just threw all the other categorical variables and provided that these should do not have unique components like complication risk. It shouldn't matter, which we confirmed down here that it doesn't matter, that these are all put up in here. And then adding the quantitative columns and then combining them into one data frame, df_regression. And so here's the name change that had to take place. And the issue was there's this space. So I just put an underscore in the name, and that cleared the issue. And this is the original code that I had in task 1, and I just felt that it was super busy, and it's what I had pulled from like data camp, what I know, and YouTube videos, and I just felt that it was very busy. So I wanted to change this and also get more practice and learn more and all that good stuff. So this is the new code. It's much simpler and not as busy, and it accomplishes the same thing as this does. So I am much happier with how this looks. So moving forward, this is what we'll be using for the model. And so I would say the largest difference between the two is this is going to be identifying our constant, where up here in the old model there was you had add constant, and you can also add it to the tail end. So this is our constant, and this is our initial model with all of our predictor variables. And so this was marked for review. So let's see, sorry, just making sure. So justify statistical based feature selection procedure or model evaluation metric. Yes. So what we're looking at primarily for a reduced model is that we're looking at our p-values of our predictor variables, and we're looking for less than 0.05. And very specifically, when we're looking at these, each time we're doing this iterative function, we're looking at the highest p-value and then rerunning the model. And so we look at the highest value, take it out, rerun the model, reassess, etc. Compare an initial and reduced regression model. And so this is the reduction process. So starting out, looking at the p-value, just went down the line and I tried to identify, so right here, so 0.902. So that was removed. And that's the case down the line, just identified the highest value and removed it. Analyze the data set using a reduced logistical model by doing the following. Explain your data analysis process by comparing the initial model and reduced model. So the values that I was looking at were the pseudo R-squared, log likelihood, the LLR p-value. And so with the pseudo R-squared value, it's a 0 to 1. It's on a 0 to 1 scale, with higher values indicating a better fit. This is largely used just to compare models. It shouldn't be used to explain variation. The log likelihood, this is a value that is a great way to measure the goodness of fit. However, all things need to be even. So we need to have an equal number of predictor variables. So I don't know if this is entirely appropriate, but the LLR p-value is similar to the p-value, and if this number is 0.05 or less, it is better at predicting the values of the response variable compared to a model with no predictor variables. And so that's what I use between the two models. And when we get to our reduced model, seemingly we have a really good LLR p-value, and this is what I will largely be looking at later on. And provide the output for all calculations. So we have a confusion matrix and accuracy calculation. So this is our confusion matrix, which I'll go into further detail here. I did add sensitivity and specificity in here, which I will come back to. And here is our accuracy. So it appears that we have a 71% accuracy, which seems pretty good, but we will come back to that as well. So with our confusion matrix, the model was true negative, 0 correctly predicted as not overweight, false positives, 2,885 incorrectly predicted as overweight when they were not overweight, 0 incorrectly predicted not overweight when they were overweight, and 7,115 correctly predicted as overweight. Provide an executable code. This will be included. Discuss the results of your data analysis, including the following elements: a regression equation. So this is my regression equation. And this is just taking our constant with our coefficients of our reduced model. An interpretation of the coefficients of the reduced model. So the constant, and I felt like some of these were kind of opposite on what I recall from the linear models, with the exception, constant. So the constant tells us the odds of being overweight when all the explanatory variables are at 0. The constant is 80%, which seems a little high, but we need to pull the data acquisition tactics used to collect the data we are analyzing. So what I mean by that is this tells us the odds of being overweight. So I took that as that's the all things 0. We have no other factors. We have an 80% chance of being overweight, which seems high. But again, I would like to understand the data acquisition methodology. High blood pressure, with every unit of change in high blood pressure, you have a 0.13 odd of being overweight, or 13%. This is what I felt was kind of opposite, because I felt like it was, with my last model with a linear regression, the total charge, for every unit of total charge, we would have a change in our coefficient. So if it was like, as our complication risk went down, our total charge would go down. So like for every unit of total charge going down, it just felt like this was opposite, and I could be reading it incorrectly. Complication risk medium, with every unit of change of, and that should be complication risk. Every unit change in complication risk medium, you have a 9% chance of being overweight. So looking at the statistical and practical significance of the reduced model. So statistically speaking, we do have some positive values here, or positive indicators that it's statistically significant. But there's more to the story than just that. So when looking at our pseudo R-squared value, we have 1737 for the unfitted model and 1068 for the reduced model, which is a good comparison metric between models. The reduced model is further from one than the unfitted model. So this indicates that the fitted versus reduced model is not superior statistically to the original. And however, so this indicates that we may not have a statistically superior model. But when looking at the LLR value, the original value is 1408, and the fitted model is 001638. So this would indicate that the fitted model is below 0.05 and would be better potentially at predicting the response variables values than a model with no predictor variables. So this indicates that our reduced model may be better than the unfitted model. When we look at the confusion matrix for both models, they are identical. So that tells me that they are both equally capable of predicting or having the same outcome. So I would say that the reduced model is not superior. But what I thought was interesting, when we look at the sensitivities and specificities, there is definitely a problem. So the reduced model has a high sensitivity towards positive rates and has a low specificity towards identifying negatives. And because of this, the quality of the data really should be questioned. Not the quality of the data, but the answers that we get from the model should be questioned. Practicality-wise, the variables selected, I would have expected more signals based on what we were trying to predict, which is being overweight. And I really thought the age, initial days, in the hospital, how long you're in there, which, if you're overweight, you may spend more time in the hospital. You may have more complicating factors. You may need more services because your case may be more complicated. I would expect overweight people to have more diabetic issues, but they were all removed from the model. And we were left with high blood pressure and complication risk medium. And that does seem to make sense, but I would also expect to see diabetes and age in that as well. So I question their overall significance in regards to our model, because the model also dropped other signals that I felt could be compared to being overweight, or used to factor in being overweight. Both models had a high prediction rate of 71% at accurately predicting someone that was overweight. And the limitations of our data analysis. So as with task one, I do have similar concerns. Regression models may be sensitive to outliers. Logistical models may be less sensitive to outliers, but the sensitivity is still present. And I would really like to understand the data collection methodologies for getting the initial data so we can understand the big picture, because when we're doing data analysis, that's what it's about. It's about the big picture. Even if we have a terrific model, we still need to have the overarching information so we can make sound business decisions. So initial model, reduce model. So data summary and implications. So recommend a course of action based on my results. So looking at like our LLR values and things like that, log likelihood, pseudo R squared, confusion matrix, sensitivity, specificity, and lack of data collection transparency. Specifically looking at our confusion matrix and sensitivity and specificity, I would be very concerned about this model and anything deriving anything significant from it. When I looked at the sensitivity and specificity, this model is not good at predicting true negatives or true positives. So that is a problem. So when we look at our accuracy, of course, we're going to have a high number, because it's not good at those predictions. We need to reel the sensitivity and specificity in, and also may just want to look at retooling the model with different variables, maybe asking a different question, using a different response variable. But as is, I would say the model is not great. And then I would also want to further understand the methodology used to collect the data so I can understand how that plays into our overall analysis. And so with our demonstration, we identified the programming environment, we compared the initial model versus the reduced model, and we interpreted the coefficients from the reduced model. This concludes my presentation, and again, I look forward to your feedback and remarks, and hope you have a good day.